Okay, these are the video solutions to the Unit 6 pretest from WebAssign. And Unit 6 brings in the concept of exponential equations. And exponential equations should be familiar from the high school realm. Uh, there's two approaches that we'll be using. The common base approach and the logarithm approach. Of course, the graphing, solving by graphing is sort of out because we don't allow the use of the graphing calculator. Question number one exemplifies a real simple situation, but it's the basic idea behind using a common base approach, right? So first of all, an exponential equation is an equation where the variable is an exponent, where the thing you're trying to solve for is a power, right? You know the base. We got a base of 2, we got a base of 64. You're trying to solve for the exponent, in this case an x. And so one approach is to get the two expressions on the left and on the right to have the same base. Right? We have a base of 2, we have a base of 64, and so your numeracy needs to kick in. And you need to sort of see that 64 is actually a power of 2, right? 64 happens to be 2 to the 6th. And now the basic idea is, since you've got the same base, no pun intended by the way, since you got the same base, and since the expression on the left is equal to the expression on the right, then the exponents must be equal. So x would have to be a 6. Right? So we're using the exponent laws to guide us in solving these exponential equations. Now, the second one, where a lot of people first had difficulty, we have 1/3 equals 27 to the x power. Now, are 3 and 27 exponentially connected? Well, that's not too big a hurdle. It should have been fairly apparent that 27 is 3 to the third power. So I'm replacing the 27 by the 3 to the third, and then that is being raised to the x power. Now, if we go back to Unit 5 and look at an exponent law that we had, and that exponent law is x to the a to the b power, then we know that that's x to the a times b power. The rule was when you raise a power to a power, you multiply the powers. And if we employ that technique right here on the right, we get 1/3 equals 3 to the 3x. And then it was at this point that we started to get a few questions from people as to how to finish this off. And so if I was going to just, instead of just show you, just sort of give you a hint, I would remind you that this 3 down here in the denominator has an exponent of 1, right? And hopefully that would be enough to get you to the idea that we did in Unit 5 of the 1 over rule. And the 1 over rule from Unit 5 said if you have x to the negative a power, if you have a negative exponent, you can get rid of that negative exponent by moving that multiplied term, in this case from a numerator to a denominator, and all it does is change the sign of the exponent from a negative to a positive. We did allude to the fact that you could go the other way if you wanted to. If you had a term in the denominator and it had a negative exponent, then you want to move it to the numerator, a multiplied term, you just change the sign of the exponent. And so it's this idea right here that is going to get us to a place where we'll have the same base. Right? So this 3 to the first, I'm going to move that to the numerator. That's a multiplied term, and of course it's going to be multiplied times 1. So 1 being the multiplicative identity, it's going to be a no non-consequence. And so we've got 3 to the minus 1 equals, on the right-hand side, 3 to the 3x. Now, we have our common base. They're both 3's, and so the exponents have got to be equal. And negative 1 has got to equal 3x. Then from there, to get the x by itself, we use the multiplicative inverse, and your answer there is going to be negative 1/3. Okay, so there's the answer for question number 2. Now, I'll make a little space and get rid of some of this, but I'm not going to get rid of all of it. I'm going to actually sort of leave these exponent laws up there. And as we turn to question number 3, we've got, right here, we've got 3 to the x plus 2 power equals 7. Now, just as a start here, um, take a moment and think about this. You know that 3 to the first power would be 3. And we know that 3 to the second power would be 9. Okay? So that gives us a general idea as to how big this x plus 2 is, right? 3 to the first is 3. And 3 to the second is 9. So since we're looking for 3 to something to be 7, we know that that something, that x plus 2, has got to be in between 1 and 2. Just as a general idea as to how big the answer to this thing needs to be. However, the 3 base and the 7 base are not exponentially connected by way of the integers. In other words, you can't obviously, from what we've just said, raise 3 to some power and get a 7. Okay? So what we're going to use here is the other technique that should be familiar from high school, and that's the technique of logarithms. So I'm going to do a log of each side, and I'm going to say log 3 to the x plus 2 power equals log 7. Okay? Now, from here, it's important that you understand your exponent laws, right? And most people in Unit 5 did very well, had no trouble with this concept right here. X to the a to the b power is x to the ab. They multiplied the exponents, right? Well, in the logarithm world, there's a very similar connected rule. It says log of a to the b power is b times the log of a. So the important thing, or maybe the way to remember this, is when you're looking at logarithms, all you're doing is looking at the exponent pieces, right? You can think of a logarithm as an exponent. And so the logarithms follow the exponent rules without the bases involved, assuming that you have sort of the same base. All right. So on the left-hand side here, where we have log 3 to the x plus 2, that's log of a to the b power. And we're allowed to take that exponent, and x plus 2, and multiply it times the log of 3. I suppose it could be said, how do you solve exponent equations? And you could say you don't. You turn your exponent equation into a multiplication equation, and then use simple multiplication, division, addition, and subtraction to solve the exercise. All right? And so now x plus 2 times the log of 3 equals the log of 7. Well, then x plus 2 is going to equal the log of 7 divided by the log of 3. That's multiplication. So all we did was divide both sides by the log of 3. And then finally, this addition, we use the additive inverse, and x is equal to log 7 divided by log 3. minus 2. So that's the technique that we're expecting that you had in a high school experience, and we're just trying to rejuvenate that um, and refresh that in your mind. Now, there is another way to write this log 7 divided by log 3. You could write that as log 7 base 3, and that comes from what's known as the change of base formula. Typically, logs are log base 10 as they're being expressed in this answer that we gave right here. But you can, and I didn't mean to make an equal sign there, I meant to make a subtraction sign. So let me get rid of that. You can then subtract the 2 from that. So this is probably the way you'd want to enter that as a base 10 log rather than think of it as a base uh, 3 log. Uh, this number right here, log of 7 base 3 or log 7 divided by 3, it should be clear to anybody again because 3 to the first is 3 and 3 to the second is 9. This number right here is between 1 and 2, right? Because the log of 3 uh, base 3 is 1 and the log of 9 base 3 is 2. This number has got to be between 1 and 2. And it's, again, based on this exponential concept. So the logs and the exponents are closely related, right? If you understand your exponent laws, then you will understand your log laws. And you will get over time so that as you look at a number like this, log base log of 7 base 3 or log 7 divided by log 3, you will get so you understand that that number's got to be between 1 and 2. All right. It takes a little bit of practice, a little bit of time, but with that practice, all should be well. Now, we'll move on to question 4 here. Keep my rules in place and just slide down the page just a little bit so you can see exercise 4. Um, and so we've got 10 to the 2x power equals 5. And at first, you might think, and again, exponential equation, right? Variable exponent. So it's what we refer to as an exponential equation. And at first, you might say, okay, how can I, 10 and 5, obviously connected. Well, multiplicatively, they're connected. But in terms of integer exponents, they are not connected. There's no way to turn a 10 into some power, integer power of 5. And so I'm going to use the logarithm idea again. I'm going to say log of 10 to the 2x equals log 5. All right. Then I'm going to use my exponent law right here again. Right. And I'm going to get 2x times log 10 equals log 5. Now, log 10. What does that mean? That means 10, because the understood base is a 10, right? That means 10 to some power is 10, right? So getting so you can read and understand this syntax, remembering how you did that back in high school. This says 10 to some power is 10. And so pretty obviously, the log of 10 base 10 is going to be a 1. The log of 10 base 10 is going to be 1. In fact, generally, for n a positive number, the log of n base n is going to be a 1. So this number right here, that's a 1. And log of 5, well, we're here on the right. And just while we're there, think about it for a second. How big is the log of 5? Well, what that says is 10 to some power is 5, right? So 10 to what power is 5? Well, you know that 10 to the 0 is 1, and you know that 10 to the first is 10. So this number is somewhere between 0 and 1. It's a decimal, right? Somewhere between 0 and 1 is the relative size of that thing. Now, back to our equation to solve, we have 2x. 2 times x equals log 5. And so to get rid of that 2 and solve that for x, you do it just the way you did it in 7th grade math. You divide by the 2. And so you get log 5 divided by 2. Final answer. Okay. So that's question number 4. We'll put one more in this video segment. We'll put in question number 5 and leave up our laws here in case we want to refer to them. And we've got what? We've got 4 plus 3 to the 5x power equals 8. Variable exponent, exponential equation. Okay. Well, first of all, 4 plus what? Right here. 4 plus what is 8. Okay? So you're using basic algebraic concepts, and you want to sort of see the structure so that things make sense to you. We know that 3 to the 5x is going to be a 4. Right? We use the additive inverse. We bring the 4 to the other side. And so we get 3 to the 5x equals 4. Now, base 3 and base 4, we don't have any exponential connection there. Certainly, it's true that 4 could be written as 2 squared if you wanted to, right? But they're the bases. They're not consistent. They're not the same. And so there isn't going to be a solution by common base. Um, and so just as well to just log both sides, and we get log of 3 to the 5x equals log 4. All right. Now we use our power to a power exponent law, which when taken in the log realm, right, log a to the b power is b log a. That allows us to take this 5x and write it as a multiplication times the log of 3. So the logarithms follow the exponent rules. That's all that does, right? And then we have 5 times x times log 3. And so can you tell what x is going to be equal to? It's going to be equal to log 4 divided by 5 log 3, right? How do you solve your exponent problems? You don't. You turn them into multiplication problems and use division to solve them. All right. So there's questions 1 through 5, a little refresher of what should be familiar from the high school realm, but may have atrophied over time. All right. And we'll be back with questions 6 through 10 in our next video.